All right, so we talked last time about the general context of AI and the different approaches, and we said that one of the beginning aspects, one of the beginning things that was done involved search algorithms, the algorithms that we now learn in an algorithms course, not things that we think of as AI. But if you think about what we said, the intelligent agent in an environment taking in information and coming up with some kind of response, it is exactly that. So the AI ideas led to, I guess it was in cooperation, right? Led to these advancements in search algorithms, and then other algorithms from there. So the our first, actually not our first lab, one of our first labs, we will go back and implement those couple of basic search algorithms that you've done before, Dijkstra's algorithm and A star. Just from the thinking about them of how we're doing this in it, what we did before is really still an AI kind of context. And so since we're a gaming class, we will add the visual that we didn't do before. Before we had CET majors and other people in there. Other majors would take that course as well, and so didn't necessarily want to focus on the graphic side. This time we'll do again just basic kind of graphical pieces, just illustrating, showing the algorithms in place. So does everyone remember what Dijkstra's algorithm is? Does everyone remember that those words exist together? So Dijkstra's algorithm is a shortest path between two points, between two nodes in a graph. Um, Again, lots of situations, lots of environments can be thought of as a graph. If there's a way to get from one place to the other, we can create an edge. The places can be the vertices or the nodes in the graph. And so Dijkstra's algorithm is a shortest path between two nodes algorithm. We typically have a particular start node, and the original intent of the algorithm was that there was a particular end node, but you can apply it all the way through and not worry about which node is the end node. And if you apply it to the entire graph, then you will have a the shortest path between that particular start node and all of the other nodes. At least, again, it doesn't give you the path, it gives you the length of the path. Right? So the algorithm returns the length of the path, and we'd have to do something else to actually get back the particular path. So you have a start node, a specified start node, and then a target, a goal, and the algorithm will tell you the length of the shortest path from that start to that target. Keep track of some extra information, and we can create the entire path. A star has the same goal. We have a particular start and a particular target. In the case of A star, the particular target is then set. It's that particular goal that you tend to think of. I'm trying to get from here to there. You need some extra information, some extra things. We'll talk about that one. Then there are other algorithms. There are things like Floyd-Warshall that do all pairs. Gives you the length of the paths between all possible pairs. We're not going to worry about that one because from a gaming perspective, we usually have, we're here and we're trying to get there, right, from this place to that particular place. All right, so just as a reminder of how Dijkstra's algorithm works, let's take a look at an example you've probably seen before, because I probably used this when we did algorithms. Um, it's a stolen example. It's not mine. It's just easy enough, small enough, and it has some interesting components to point out. So let's say we have have a graph with a set of locations here. This graph for Dijkstra's algorithm is going to have positively weighted edges. The way the algorithm works, all the edges are positive weight, or at least the original intent of the design. Let's say we're going to start at A, and our target is F. All right. But what do we have? We have some weights associated with each edge. And so what the algorithm takes into consideration is we're at the starting point and is going to assign a label to each one of the other potential places that tells the shortest distance from here to there, at least the shortest distance so far. Right? And so, so right now, how far is it from A to A? It's 0, right? You can get there with no effort, because that's where we're starting. Right now, since we haven't done anything, all of the other locations have a label of infinity. Right? All of the other labels they're far, far away at this point. So we're going to analyze each vertex one at a time in a particular order. We're going to, we'll talk about that in a second. But we're going to update the distances to the neighbors of that vertex. And as we update the distances to the neighbors, then we say, we assign a temporary update to those, right? It's a temporary update because you might find that there's a different way to get there later on that was even better than the one that you had found earlier in the process. So we will, first of all, begin with this vertex A, and we're going to look at its neighbors. So we look at each of its neighbors, the nodes, the vertices that are adjacent, and we can do this in increasing order of weights. So we have these edge weights. So we're going to look at from A to B. How far is it from A to B? It's 7, and 7 is less than infinity, I think. So we're going to update the label there to 7. We're going to look at A to C, update that label to 9. A to D, update that label to 14. At this point, vertex A is done. We have used all of its information. Now, thinking about this from the perspective of an intelligent agent, what does it have? It knows where it is, and it can access this information from the environment. So it's utilizing that information and accessing or updating other information. Now we're going to consider from here. This does not mean that the agent has moved to that location, because that might not end up being part of the path that gets us to our goal. But the agent is using the data that's available from that location. All right, so from this location, we now have, well, let's look at what we have. Which one do we consider next? I said that one, but I didn't say why. Each of these has a value associated. 7, a 9, and a 14 now are the labels. We're again going to go with the lowest label. So we go to B, and we look at updating the adjacent pieces. So we don't look back at the one that's already done, right? This one's finalized, it's closed. So from B to C is how far? 10, but to get to C that way, we will have had to go through, or from A to B to C. So the value that we consider is this value plus that one. Right? How far we've come so far, plus how far else would we have to go on from there. So this is 17, which is greater than 9, so we don't update that one. Right? We leave that be. But what do we do with that? Update that to 22. Now, our goal was to get from A to F, and we have a value on F, but that might not be the smallest, so we don't say, oh, distance is 22. But B is finished. Now, the labels that are out there are 9, 14, and 22. So C is next. We look from C to D. It's going to update the 11 or 14 to be 11, and update F to 20, and now C is complete. We have 3 labels at this point. An 11, I didn't mention them earlier. We have an 11, a 20, and an infinity. Right? We had the infinities before as well, but we were ignoring those. So we have the 11. That's the next one. What do we update? The infinity is changed to 20. And that one's finished. Now we have 2 labels left. All right. Nothing would get updated with either of them, but where does the algorithm actually go? The algorithm has to make a choice of which one to consider. And so maybe then, since they're the same, we do it by alphabetical order, and it would check. But there's a way to slightly improve the algorithm and say, as soon as your target becomes eligible for next, the algorithm can stop as far as going to that target. Right? But if we updated and say, okay, well, what's next? Well, these 2 tie, so we break the tie by this other kind of alphabetical order. So we check E. E doesn't update that. E's finished, and now F is the one that's up. So then we can check F. If we really carry it all the way to the end of the algorithm, we check F. There's nothing to update, and the algorithm completely finishes. So what do we have? The labels give the length of the shortest path from A to that place. What do the labels not give? Or what does the algorithm not give? The algorithm does not give the actual path that gets there. But the purpose of the algorithm was not to give the path. The purpose of the algorithm was to give the length of the path. But what could we do to get the actual path? Yeah, so how would we, what information would we use to get the previous node? What? Yeah, so anytime you update the label, you say, this is the node that caused that update. Right? This node caused that update. If you update it again later, you replace that, right? This new node caused the update. And then what do? When you get to here, you say, okay, which node caused this update? Go back to it. That's the last step in the path. That node, which node caused its update? You go back. Which node caused its up? And you keep going until you get to the start. And then you have your path. You can reconstructed it in reverse order, and you have it going the other way. Right? So that's familiar, right? And you've written it before, but we're going to write it again, this time with a graphical component where we're illustrating what's happening. What happens as you're considering a node, while it's under consideration, you change the color or something, right? And when it's finished, you change the color again. The labels that are temporary maybe show up in one color, and then the labels once they're finalized, they've changed to some permanent value, whatever. And then when you finish it and you reconstruct your path, reconstruct it backward and show what's happening to see the path, right? And then so what would the path be in this particular case? Right? Which one caused this update? This update was caused by C. And C's final update, which was only one update, but its last update was caused by A. And so the path is from A to C to F. All right. So that's not new, but maybe a refresher. What is different between Dijkstra's algorithm and A-star search? Yes, well, okay, so A-star takes into consideration two pieces of information. Dijkstra's algorithm only looks at how far we've come so far and keeps going to the shortest places so far to explore next. A-star considers not only how far we've come, but how far we think it is to the target. So there's this how far we've come so far plus a heuristic. Right? A heuristic involves an estimate of the distance to the goal. Now, where do you get an estimate of the distance to the goal? Well, this estimate turns out to always need to be an underestimate. So in some cases, if this were a physical map, then a straight line distance would be an underestimate, right? So we could measure, okay, what would it be in a straight line? And I'm looking around. Maybe do um, we'll do a little bit more background on A-star before we do a lab on it. I have a previously recorded video on Dijkstra and on A-star on the YouTube channel, so you can take a look at those. I'll give you the link for those, just as a refresher to see a little bit more detail. So you have this idea of how far have I come so far, plus how far do I think I have to go to get to the goal. So what this would do is, the difference between these two is if I had a starting point here, and let's say my target was over here, and then there's a whole bunch of stuff over here, and then there's stuff in between as well, right? There's stuff in both directions. Well, what would Dijkstra's algorithm do? Dijkstra's algorithm is going to go to whatever's closest. So we're going to be over here. And it might spend a lot of time looking in this direction before eventually going in this direction. Imagine that this space is a lot bigger than these spaces. So with Dijkstra's algorithm, we might have to explore this entire side before we say, okay, it wasn't over here. Let's look in that direction, right, the target. Whereas A-star takes into consideration not only how far away we've come from the start, how far we've already come, but how far we think it is from there to the target. And we get that information, again, from an external source. So the intelligent agent learns this information from somewhere else, or is provided this information. Right? Here's an overall map. We're trying to figure out the best way to get there. So what happens with A-star is, yeah, we might look this way a little while, but eventually our guess at how far it is back to the target tells us stop exploring in this direction and start exploring in that direction. So we have not only the how far we've come so far, but we get an extra label that says how far do you think it is from here to the goal, this heuristic value. And so what we do over here is we just minimize the values of so far. How far have we come so far, right? So we're minimizing how far we've come so far. And over here, we're adding that together with how far we think it is onto the goal. And so we want to look at minimizing both when we consider the next node, right? When we consider this node, we considered it because the values at the time were 7, 9, and 14. So that was the next one up. But if this had been really far from the target, maybe one of these others would have won out. If we had guessed that, let's say we had guessed, or we knew from some other information, that it was at least 14 to the end from here, and at least 10 to the end from here. If we had the information that says from here to there is at least 14, from here to there is at least 10, maybe more, but at least that, then what would we have considered next? Instead of considering the 7 plus 14, we would have considered C as the next node, 9 plus 10. And we could have gotten to the target sooner. Does that make sense? So this considers, when you're choosing which node to consider next, it looks at not just how far we've come so far, but how far we've come so far plus how far we think it is to the goal. And the how far we think it is it's at least this far. Right? Maybe more, but it's at least this far. And so what this can often do is it still gives the same answer, right? The shortest path is still the shortest path, and both of these algorithms always give us the length of the shortest path. But A star can sometimes get there with fewer analyzing nodes that aren't really relevant. Okay, and so what we will, again, do is we'll have a lab where we implement both of these and see what the differences are in a visual way, rather than just analyzing them from a completely theoretical perspective, or even analyzing it on a particular graph and see what's happening. We'll just be able to visualize that a little bit better. All right. Thinking about it again from the perspective of the intelligent agent, it is using the information that it's getting from the environment, and it's also using, in the case of A star, some preliminary information that it was already given, right, in terms of or that we create for it, right, a heuristic, a guess as to how far it is. Not which direction, but just how far things are away. But this, you can see that it could build as it got to locations. Right? If these numbers are waiting there, the agent can access the relevant points, and then when it gets to that location, measuring or accessing that particular information. Again, not necessarily physically going there, but being able to access the appropriate data. What would happen at the end of Dijkstra's algorithm if there was still an infinity label? What does that mean? Yeah, that means that you can't get from this point to that one. If you finished the algorithm completely, it would tell you, and you still had an infinity label, it would tell you that you can't get from here to there, as long as you implemented and carried out the algorithm correctly, right? And updated it. So if it's carried out correctly, what does Dijkstra's algorithm do? We'll give you the shortest path between two nodes, as long as they're in the same component of them. So it's really designed for a connected graph where you can get from here to there. What would have happened if we weren't trying to get to F, but instead we were trying to get to D? We just stopped sooner when D was the next one up, right? When D was the one that we were going to consider next, we would have looked, and its label still would have been 11. And we go back, right, and construct the path, which the path from A to D goes where? Still through C, right? Even though C is farther away from A than B is, the shortest paths go through C. What about the path from A to E? it also goes through C. So even though C is further away than B, all the paths go through there, except for the path to B itself, right? The path straight to B, everything else goes through C. Almost, right? Except for that one part right there. Um, okay. So there are other situations that don't necessarily look like a search problem that we can interpret as a search problem. So often what we will do is we will imagine the set of all possible solutions to a particular problem is some space. And then we want to search through that space for the actual solution to the problem. And so how we search through a space, well, that will differ. What is one way to search through a space? One way to search through a space of potential answers to find an answer is to try everything. So in that case, brute force becomes a search algorithm. I guess it always is, but we don't think of it that way, right? But try everything is searching in a very, it's very methodical. If you try everything, will you find an answer if it exists? Yeah, you will eventually find an answer. What if there's more than one answer? If you try everything, you'll find all the answers. What if you try everything and you don't find any answers at all? Then there wasn't an answer, right? So brute force works. Again, what we know the obvious limitations and the problems with that. If the search space is very big, then that can lead us to untenable situations. All right, but there are other things that don't necessarily look like search that turn out to be search. So we will see this quite often in terms of what we're going to do through the term. A lot of things that we would not typically think of as being a searching problem, really genetic algorithms turn out to be a search problem. All right, so let's talk about a problem that on the surface doesn't look like a search problem. And you probably, I think most of you have seen it before. We have 4 people on one side of a river. There's a bridge, and these 4 people need to get from this side to that side. Now there's extra things on this in terms of this particular problem. It's not just search. There are constraints, so it's part of a different category as well. We're going to see it from a different perspective uh, as well, or we'll think about it from a different perspective as well. But 4 people on this side, say A, B, C, and D, they all need to get to the other side of the bridge, but the bridge has limitations. The bridge can only hold 2 people at a time, and it's dark, so you need a flashlight to get across the bridge, and we only have one flashlight. And its batteries are almost dead, so it's very dim. But there are holes in the bridge. I mean, it can only hold 2 people at a time, so it's old and in bad shape. And so you can't just like stand in the middle and shine the light for someone. You have to be with the person, right? Somebody's carrying the flashlight, walking across the bridge. It's too far to throw the flashlight back or anything like that, right? No tricks there. It's 2 people have to take the flashlight over. Somebody has to bring it back. 2 people have to go over, on and on, right? Until everyone ends up on the other side. Person 1 can cross the bridge in 1 minute. Person 2 can cross it in 2. A and B. C can cross it in 5. And D needs 10 minutes to cross the bridge. All right, so we've seen this before. Do you remember a solution? Yeah, so when you're crossing, say I didn't specify, but I mentioned they have to go together, right? So if you're going together, to get across the bridge, even if, say, A and D are crossing together, it's going to take them 10 minutes to get over, right? Because one of them is carrying the flashlight, and they have to walk together. All right, so what's the fastest they can get across? So that's the question. How is that possibly a search problem? Okay, so we could turn it into a problem somehow, maybe like this. It's a graph problem in some way. Um, how else could it be a search problem? Hmm? Searching for an answer. In the idea that I just mentioned about it being, about brute force, we could list every possible way that they could get across, and just check every one of them for the shortest time, right? Right. So yeah, each bridge state, and how long does it take to get from this node to that node? Um, all right. So everything can be turned into a graph problem. I think just about everything can be turned into a different kind of problem. Now, it's not always beneficial to do so, but it can be. It can be done. So let's see. How long will it take these four people to get to the other side of the bridge? And they all need to be over there at the same time, right? So they're all going to the other side and then going on their whatever their quest happens to be. 19. All right. So A takes everyone over. So that takes 2 minutes to go over, a minute to come back, then 5 minutes, and a minute to come back, and then 10 minutes. So you think 19 minutes is the best option? What kind of solution is that? What kind of method is that? It's a greedy method, right? Because using the best possible at the time, or what appears to be best possible at the time, the fastest person taking everyone over. Is that the best answer? So one of you remembers what to do. There's a way to do better than 19. Can you get 17? What do you do? Yeah, they have to come back, right? Somebody has to bring the flashlight back. Yeah, we somehow, that would be nice, right? Because we don't have a 10 plus a 5, then we only have a 10 involved. So is there any way at all to get C and D together on this? What would we have to do to get C and D going together? What would have to happen before that? See, if C and D go first, that's 10 minutes to get over, and then if C comes back, that's 5 more minutes, and then C has to go back again, so we're already at 20 minutes, right? So we want C and D maybe to cross together, but not first. So the only other option is for A and B to go over. So if A and B go over, how long does that take? 2 minutes. So if A and B, well, let's do it this way. Our situation at that point would be A and B over there, C and D on the left, and that would have taken 2 minutes. Then A comes back, takes a minute. Then C and D go over, which takes 10 minutes. B comes back, which takes 2 minutes. And then they go over, which takes 2 minutes. And altogether, 17 minutes. Can we do it better than that? What if what? So you're saying, what if instead of A coming back, if B came back? Or let's check it. So A and B went over. Now what if B comes back instead? And then C and D come back. And then A goes back, which is a 1. And then they come back, and it was 2. So what happens? This 2 and this 1 swap places. Yeah, so we can switch one of them out, but then the other one switches to the other, right? So is there any way better than this? Are there any ways worse? So in our search space, let's let D take everyone over. And then in between, let's let D just walk back and forth sometimes just because it's fun. Right? That's it. That's a possible solution, but it's even worse. Right? The bridge breaks. Well, so that's not in the search space because that's not a potential solution. Right? A potential solution has to follow the rules, no more than 2 at a time. But yeah, so what would happen? What if somebody went halfway? Then the other person that's coming back would have to have the flashlight, so that person can't move. And they can't bring anyone on, so it would just have to be somebody else coming onto the bridge with the flashlight then. So it could, in certain other situations, it could conceivably be a valid kind of thing. Take somebody part way. There are versions of this kind of problem where you're trying to get, you have like a headquarters, and you have a particular outpost that you're trying to get to over here, and you can't drive from here to there because it's too far. So what do you have to do? You have to take fuel to different points along the way. But you can only take fuel so far because you have to be able to get back. So you take the fuel out to there and come back, get more fuel, take it to there, refuel to go further, to be able to come back to here to finish fueling, to get back to here to refuel some, or to get back all the way back to here to get more, right? All that kind of thing, going back and forth, right? So there are versions where going part way and coming back might be beneficial. On this particular problem, going part way and coming back, or somebody else coming back, seems to add to the... But is it still part of the potential search space, the potential solution space? Yeah, those could be part of potential solutions. Just the person who's on the middle of the bridge just has to wait. All right, so what's going on? We're going to implement this. This is actually lab 1, to be able to get the walking times of people as input. So first of all, starting with this one, but get the walking times of people as input, and then output the fastest time and how to do it, right? Ultimately, how to get from here, how to get everyone from here to the other side, who should do what at what moments. All right, so we will take some time thinking about Dijkstra's algorithm in A star and implementing that in a lab. But for right now, we want to see what happens with 4 people crossing with different times and trying to figure out. You don't know the times until runtime, right? So how long each person takes, you learn that at runtime, and we want to calculate the fastest possible way to get everyone over. Well, will it always be on the lines of 2 fastest and then 2 slowest? It, yeah, it depends on the. It could depend on the speeds that people cross at. Right? There might be certain points. There might be some place where it's like, oh, if they're this close together, then this way is better, or if they're this way, then the other way is better. Could there even potentially be a third way? Could it ever be that it's faster for somebody else to be the runner for a time and somebody else? We don't know for sure, right? And that's part of what we want to try to do in at this point. So we're going to be thinking from the perspective of the agent. We get the information, and we're trying to figure out how to get everyone over. Um, will it always be this kind of thing? It could be, but it potentially could be the fastest person takes everyone over. All right. How many ways, how many solutions are there to this particular version of the problem? In terms of a solution here is how do you get everyone over? Sorry? Are there infinitely many ways to get? So how do we get everyone over as quickly as possible? That's the thing, right? How do we get everyone over as quickly as possible? How many solutions are there? Well, at least 2, right? We have 2. Are there more than that? No, I think we could convince ourselves that these are the 2 solutions. Now, as far, again, coming back to Dijkstra's algorithm idea, if the question is just how long, there's only one solution. Right? What's the fastest? There's just one. If we say how do you do that, then there are 2, but they're not really different, right? But they are different. When A comes back or when B comes back, they change, so that is different. But conceptually, it's the 2 fastest people walk together and the 2 slowest people go together. So in one way they're the same, in other ways they are different. All right. So we have the lab. We'll stop with content today then, since A star and Dijkstra we're going to need some more thinking about. But I want you to let's work on this now together while we're all in the same space, so you can ask questions if you have any. There might be typos on the lab. We want to take care of those while we're all here together.